The Crab Nebula has stimulated an intense study by astronomers for decades. In fact, modern astronomical observations reveal many phenomena so strange that our efforts to understand them take us to the frontiers of our present knowledge, and for some, to the world of science fiction. To explain many of the energy sources now known requires all that Einstein's theory can tell us of compact, collapsed objects, and may involve the most bizarre consequences of his theory. But what does relativity theory say about these objects and how they came to exist? To explore the answers to these questions will involve us in a flight of fantasy, a stretch of our imaginations. Meet Alan Cooper.
What do astronomers mean by a compact object? They relate it to the effect of the object on light. The sun, for instance, deflects light, but the angle of deflection in that case is very small. But imagine that we could compress the sun. Then the deflection of a ray just grazing the surface would get bigger. And sending out a light beam from the surface at various angles, it also would be bent. Nearly 200 years ago, in 1796, the French mathematician Pierre Laplace imagined a body so compact that the light could not escape from it at all. He thought that should happen when the escape speed, that's the initial speed which something has to have to overcome the gravitational attraction of a body, when that escape speed is equal to the speed of light. In other words, he was thinking of light as particles which could be held back by gravity. And he saw no reason why the universe should not be littered with these dark bodies with light trapped inside them. Well, nowadays we think we understand light and gravitation rather better. But in fact, we still do the same calculation to find the mass and radius of a body which can trap light. Doing that calculation for the sun, we find that it would have to be compressed to a radius of about 3 kilometers to trap light. And what about other bodies? The Earth, for instance, would have to be compressed even harder to end up about the size of a golf ball, a radius of about 1 centimeter. We could keep on making that calculation separately for a whole range of objects, but to do it more systematically, let's mark off mass against this axis and radius against this axis. And then with the right choice of units, our sun would be here, and our imaginary compression would take it at the same mass down to a radius of 3 kilometers. And for the Earth, it would start here, and our imaginary compression takes it down to the special condition which Laplace imagined. So for each mass, there's a special radius, and this traces out a dividing line. In the sphere, at that radius, we call the event horizon, and the space within that event horizon is what we call a black hole. Now, all astronomical bodies have their place on this diagram. For instance, this large globular cluster of stars, much more massive than the Sun alone because there are tens of thousands of stars in it, would appear here. And still more massive, a complete galaxy would appear somewhere up here. So that's what relativity says about the dividing line between the two worlds, the one we can see and the one we can never see. Laplace could do little more than guess at what strange properties they might have, because he only had Newton's law of gravity to work with. But general relativity, on the other hand, tells us exactly what black holes should be and what properties they should have. And it even gives some hint about how they might have been formed. But only astronomers can tell whether, in fact, such exceptionally compact bodies really exist in the universe. The record for the highest observed density of matter has been broken several times in the last 100 years. In 1844, it was noticed that Sirius, the brightest star in the sky, displayed small wiggles in its motion with respect to the background of more distant stars, which showed that it was revolving about an unseen companion as it moved along. 19 years later, the faint companion of Sirius was observed for the first time through the telescope. The two stars mutually revolve around each other with a period of about 50 years. Application of the law of gravitation shows that to account for the observed revolution, the companion star has to have a mass roughly like that of the Sun, but its size turned out to be 100 times smaller than the Sun. Such stars have become known as white dwarfs. A white dwarf of solar mass doesn't collapse even further to become a black hole because the pressure of the electrons prevents it. But stellar evolution theory predicts that when stars rather heavier than the Sun collapse, the electron pressure cannot hold them up, and the collapse must then continue to still higher densities. It's thought that the result is a new type of star. Theoretical physicists had predicted in 1930 that when the electrons get forced to combine with protons to form neutrons, that the pressure can again be supported. But astronomers had to wait until 1967, when rapid pulses were observed from a new type of radio source. Of the many such sources, one of the fastest is in the Crab Nebula. The radio pulses are extremely regular, which suggests that they come from a rotating or vibrating body. But the short period meant that something new was involved. Even a white dwarf could not rotate or vibrate that fast. It would simply fly apart. But there's a lot of energy in the radio pulses, and that must derive in some way from the rotation or pulsation, and so slow it down. And yet slowing down is very gradual, so gradual in fact that it was difficult to detect. A star is needed to store that much energy. But what sort of star could cause that flashing? A rotating star of about a solar mass, but an extremely dense star made of neutrons, the type of star envisaged 30 years earlier, fitted very well to the short period combined with massive amounts of rotational energy. We believe that the magnetic properties of such a neutron star can make it emit a beam of radiation that's flashed our way with every turn. With that model, the Crab pulsar falls here, much closer to the dividing line than a white dwarf, a radius of about 10 kilometers for one solar mass, but still falling short of being a black hole because the neutron pressure can still support the mass of the star. But stellar structure theory says that a neutron star cannot be stable if it's more massive than about 3 solar masses. If it does have higher mass, we think it must collapse and form a black hole. We need a way to find such massive, compact objects, and the best way we know is to look at double stars. An analysis of their mutual revolution can yield an estimate of their masses even if one is invisible. Remember the path of Sirius. It's the same story over again. But how can we also tell if the second star is a collapsed object? Often, when the two stars are close together, gas blown off the surface of one can fall onto the other. As it falls, the gravitational energy of the fall will be turned by friction and turbulence into heat, in just the same way that the water at the bottom of a high waterfall is a degree or so warmer than the water at the top. But the temperature rise for matter falling onto a collapsed object will be far, far higher. Before it reaches the event horizon, the gas should be so hot, 100 million degrees or so, that it will give off X-rays. Most of the gas will be swirling around the star as it falls in, and so be flattened into a pancake of gas called the accretion disk. The accretion disk will be too small to see directly, but the X-rays are the clue to its existence. George A. Bell.
So to have a candidate for a black hole, we must first find a star that is gravitationally attracted to an unseen companion in a binary star system. Secondly, analysis must show that that companion has a mass that's greater than is allowed for a neutron star. And finally, to assure that the object is a tiny collapsed object, we have to see X-rays coming from hot gas, that's falling into it. Now, there are several such possible candidates for black holes. Among them is Cygnus X1, which is the first X-ray source to be discovered in the constellation Cygnus. The visible star is an ordinary bright star, but the spectroscope shows that it has a motion about an unseen companion that must have a mass around 10 times that of the Sun. And moreover, it's a strong source of X-rays, as can be seen from this X-ray picture. We cannot be absolutely certain, but many astronomers think that Cygnus X1 probably is a black hole. The visible component reveals little sign of the bizarre nature of its binary companion. But let's suppose that the companion really is a black hole, and let's imagine what a trip into it would be like. Our intrepid astronaut, Alan Cooper, is about to take such a trip, where he will encounter distortions of space-time on an extreme scale.
To show up those space-time distortions, I'll use a pair of flashing lamps run by an atomic clock. One of them stays at home base, and the other one comes with me. And I'll set off towards Cygnus X1 with a short burst of the motors so that afterwards I can fall freely towards it. The first thing you'd notice is that the flashes get out of step. My lamp is lagging behind yours, and the light is slightly reddened. These are effects due purely to my movement. They're Doppler effects. Remember, I'm falling freely, and so everything is normal for me. The laws of physics are the same for all freely falling observers, and that's certainly what I am now. But for your observations of me from home base, a new effect comes into play. It's the gravitational redshift, and it means a further lengthening of timescales for light and for everything else which you observe in this spacecraft. The corresponding distortion of space shows up if I send a light out sideways. It starts off in a straight line, but over bigger distances, the curvature effects due to gravity make its path to you appear bent. All this time, I'm in free fall, traveling towards Cygnus X1. As I get closer to the black hole, the gravitational distortions of space and time will get more and more extreme. And if I can survive the journey through the accretion disk, they'll soon be noticeable even between one end of the spacecraft and the other. The difference in gravity stretches my feet down away from my head, and I could do a gravitational redshift experiment right here in the spacecraft.
We, in fact, have an enormously lengthened view of Alan as he reddens, fades, and disappears. All matter falling into a black hole seems to freeze at the event horizon. Therefore, stars collapsing into black holes are sometimes called frozen stars. To Alan, though, his time is normal, and although we could never see him, he passes right on through the event horizon. In this reconstruction, in Alan's space-time, forever hidden from us, we see him fall to the black hole's center, where general relativity predicts that he will reach zero size and infinite density. Mathematicians call such a point a singularity, but many physicists doubt that physical singularities of infinite density can really exist, and expect that new physical theory may eventually come to light. Anyway, there's nothing mysterious about a star collapsing through its own event horizon, and Cygnus X1 is the best candidate we have for a black hole. Now, an object does not necessarily have to have extraordinarily high density to become a black hole. A small mass black hole, if any exists, does have to be compressed to very high density to become a black hole. But the size of the event horizon is proportional to the mass of the object. So a large mass object could become a black hole without necessarily getting higher densities than those normally encountered. The most spectacular phenomena that many astronomers believe are associated with black holes were discovered with radio telescopes. Since World War II, many such systems of radio telescopes of ever greater complexity and even worldwide networks have been constructed to provide an ever greater detail of the radio sky. The 8 antennas in the 5-kilometer array of the Cambridge Radio Astronomy Observatory are mounted on the old Oxford-Cambridge railway line so that their separation can be varied. Such large arrays have the advantage that they can pinpoint the precise directions in the sky and the sizes of radio sources. Many galaxies that appear ordinary on photographs made in visible light are found to emit astonishing amounts of radio energy. Frequently, the radio sources are great clouds of ionized gas on either side of the galaxy, and hundreds of thousands of light years from its center. The radio waves are emitted by electrons in the gas, spiraling about lines of force in a magnetic field at speeds near that of light. But how did the gas get out there? And how did the electrons get their high speeds? Most extreme among these radio sources are the quasars. On an ordinary photograph, a quasar looks like an insignificant star. But the spectra show them to be moving away at exceedingly high speed, many of them at more than 90% the speed of light. Their innocent stellar appearance, then, is illusory. In fact, quasar is short for quasi-stellar radio source. Most astronomers think that quasars are energy from violent activities in the centers of galaxies, too far away to otherwise be observed. But what then is the power source for these radio galaxies and quasars? Many investigators believe that there are very massive black holes in the centers of the galaxies, where gravitational energy is released by the infall of amounts of matter equivalent to hundreds of thousands or even millions of suns. An example may be in a galaxy called M87 in Virgo. Recent observations indicate a great central source of energy that could be due to a black hole. If quasars are due to black holes in galaxies, most of them must have formed long ago when the galaxies were quite young, because most quasars are extremely far away, which means that we see them by means of light that left them in the remote past to begin its long journey across space to reach our telescopes. So quasars occurred at an early epoch in the universe and have long since ceased to exist. But if quasars don't exist anymore, their power sources must have been temporary. Perhaps we can understand this, though, if black holes are responsible. Because as black holes accrete matter, they grow in size. Eventually, the hole is large enough that matter does not have to reach especially high densities before it falls in. Then there's no way for the matter to heat up and get rid of that energy by radiation. So if this idea is correct, eventually the black hole power source turns itself off. Our own galaxy may well have an aging black hole, large and relatively inactive, at its center. But now we are on to questions where astronomers are speculating at the limit of their observations. What about the theoretical speculations at the limit of general relativity theory? Alan Cooper.
For the effects of gravity over large distances, general relativity gives a good understanding, and maybe it works well also for matter at high densities, such as might form black holes. But that leaves the problem of the behavior of matter over very small distances, such as inside the atom. And for that, physicists use a quite different sort of theory, described in the language of quantum mechanics. But it's all the same space and time, even if it's, as it were, chopped up very small inside an atom. So it's worrying that there's such a large gap, or seems to be such a large gap, between relativity ideas and quantum ideas. There should be some link between them. Now, black holes can be very small if they're extremely dense, so maybe there's a link there. The British physicist Stephen Hawking thinks there must be such a link, and that it should show itself in a new process, part quantum, part relativistic. The quantum part starts off from the fact that, as has been observed very often, when energy turns into matter, a particle-antiparticle pair is produced. It might be an electron and a positron, or it might be proton and antiproton. There are many possibilities. Now, one very special way of supplying that energy is to take it from the intense gravitational fields around a very small black hole. That's the relativistic part of the idea. Now, one of those two particles will probably fall into the black hole, so the other one will apparently be emitted from the black hole, and that's the new process. Black holes should evaporate, although Hawking's calculations show that that will only be detectable and measurable for very small black holes. Now, nobody yet has thought of a way that these mini black holes could be produced in stars, but they could be produced in the Big Bang, which we think was at the origin of the universe and started its expansion. So maybe there are mini black holes all around us, but we don't know yet if there are. These theoretical ideas are at the frontier of our current understanding. At the same time, there's a growing awareness of the great diversity of objects in the universe, as revealed by new types of telescopes like the orbiting X-ray observatories, and by new techniques that enhance the effectiveness of great optical telescopes like the 5-meter reflector on Palomar Mountain. Above all, the combination of evidence reveals processes in these newly discovered objects which we can only understand through the ideas introduced by Einstein more than 50 years ago. Theoretical and experimental advances go hand in hand in science. Experiments often suggest new theories and always serve to test whether a theory is in accord with the real world. But I think it's interesting that in studies of space and time, theory has often been in the lead. By pure thought, men have been able to single out the way that the world can be expected to behave. That can only happen if there's some underlying simplicity. We seem to be remarkably fortunate that the laws of nature don't have arbitrary and unmeaning complexities which would mean that we could never fathom them out. Einstein summed up all of that in one sentence. The most incomprehensible thing about the universe is that it is comprehensible. We live in a world which is simple enough to be understandable. The laws and constants of physics are unchanging, and they're universal, so that wherever we delve into different areas of physics, whether relativity physics or quantum physics, we will find, we think, eventually, different parts of the same structure of space and time.